All right, we are going to pick up where we left off. We are apparently ahead of Dr. Batari's section by actually quite a bit, so we might.
Dude, the lab yesterday, the 4 people in Batari's class.
Yeah, we had to go through like an entire lecture to get to. We were all like, ready to start. Okay, so some people may not know what we're doing today.
Yeah.
I pulled out my notes and I was like, oh, it's not that bad.
Yeah.
Exactly.
So we're very likely going to knock off a little bit early to let him catch up. So happy Friday. Yeah, I do the lab with them on Wednesdays, and I was like, oh, this is like we did exactly this. Like exactly that. Yeah. All right. So let's see. Let me make sure what's going on in chat is just people telling me that they're here. That is what it looks like. All right. So we left off at a terrifyingly obscure looking result. Yes. We're gonna +1. Yes.
I can assume that everything is larger than everything. You just cancel it all out.
Not even close. All right.
Are you now gonna give us like the easy?
So we have to finish the hard way before we talk about the 2 different easy ways. We're close. We literally we are almost there. We are going to have to make one assumption, but we'll get to that in just a second. Just one. Just one.
We just ignore the +1. Write it all again.
All right. Okay, so this is what we have. We have something on the top that it should be pretty easy to see that we have a pole at GM over CGD. And then we have that horrifying denominator that is a function of S. So we can see, obviously, that it is S squared times some horrifyingly large coefficient plus S times some equally horrifying coefficient +1. So if you recall, our our high frequency HF of S was going to be of the form 1 plus S over omega Z1 times 1 plus S over omega Z2 all the way out to omega Zn. We don't have a whole heck of a lot going on with our zeros, so this one's pretty easy to figure out what's what. And then in our denominator, our high frequency transfer would be 1 plus S over omega P1 plus 1 plus S over omega P2 times 1 plus S over omega P sub n. We only have 2 poles because we have a factor of S squared. So I can say that, let me get my notes here. A to the S squared plus B to the S plus 1 is simply the product of 1 plus S over omega P1 times 1 plus S over omega P2. If we FOIL this guy out, what we're left with is S squared over omega P1 omega P2 plus 1 over omega P1 plus 1 over omega P2 times S plus 1, which means this big ugly thing right here is A, and this big ugly thing right here is our coefficient B for our quadratic equation. So that tells us a couple of things. All right, first, A is the product of the reciprocal of the poles. So it's going to be really hard to extract out what any one individual pole is from that guy. B is the sum of the reciprocals of the poles. So it's going to make it hard to extract anything either. So our assumption that we are going to make is that one of our poles is dominant, meaning that it's occurring at a much lower frequency than the other poles. In that case, 1 over omega p1 plus 1 over omega p2 is approximately equal to 1 over omega p1, which tells us then that omega p1 is simply 1 over b. All right, so that is the assumption that we're going to make. So our first pole frequency then is equal to, let me make sure I'm writing this right, 1 over 1 plus GM RD times CGD RThev plus RD times CGD plus CDB plus RThev times CGS. So that is our first pole. And we should be able to see, now that we know what omega p1 is, we can figure out what omega p2 is, since we know that A is the product of the reciprocal of the two poles. So that means that omega p2 is going to be B over A, which is going to be 1 plus GM RD CGD RThev plus RD CGD plus CDB plus RThev CGS divided by RThev times RD times CGD CGS plus CDB CGD plus CDB CGS. So we have our two poles, and then we can evaluate it. Let me just put this here, absolute value sign. Lastly, we have our single zero, which I said before we can get by inspection just looking at our numerator, and it's going to be GM over, let's see, CGD. All right, so let me pull up our simulation here real quick. If I can find LT Spice, there we go. No. Open high frequency response. All right, and we're looking at this from 1 meg to 100. And right now I have R sig at 500 ohms. So meaning that we have some source resistance. So if I run this simulation, let's see, add traces. we have a fairly good argument for our dominant pole approximation. Oh, let me make this not green so that you guys can see it. So this guy looks like a first order low pass filter, right? This has one distinct roll off, which is telling us that our approximation of a dominant pole is effectively correct. If the two poles were close to each other, we would see something like what we saw on the low frequency side, where it was a ramp and then a step and then a ramp and then another step. But our first pole is significantly lower in frequency than our second pole, so we're getting exactly what we should really expect from this guy. If we change our signal resistance to 1 micro ohm, this is going to look effectively the same, but it's just going to slide our response over a little bit, and it's going to push our second pole even further away. It'll actually be at very close to infinity. So right now, we're having a 3 decibel frequency at somewhere around 25 megahertz. We've effectively moved the 0 over when we zero out that guy as well, which is why we get this flattening here. And our response is still, yeah, it still looks to be around 20 something megahertz. And this is effectively what our models would predict for these particular values. But we're just seeing what the effect of having a large signal resistance versus a small signal resistance would do to this guy. All right, so that is the hard way. I would highly suggest you guys never ever do it that way. Okay. We are going to use this to do some direct comparisons though with the 2 different easy ways. So the first of our 2 different easy ways is going to be the method of open circuit time constant, okay? So when we're looking at low frequency signals, we use the method of short circuit time constants, meaning that we look at each individual capacitor and associate a time constant with it while we set all of the other capacitors to be short circuits. At high frequencies, we are going to do the exact same thing, except we're going to set all of the other capacitors equal to open circuits. And the response equation for our estimation of where the mid-band ends is slightly different, okay? So method of open circuit time constants. High frequency only. All right, so as I said, we're going to analyze the circuit with Vn is equal to 0. So we short out our input signal again and determine the resistance seen by each individual capacitance with the other capacitors open circuited. So we're assuming that the frequency is low. Our capacitor of interest is behaving like a finite impedance, and all of the other capacitors, we're assuming that the frequency is low enough that they look like open circuits, is effectively what's going on here. Our estimation for omega high down is going to be 1 over the sum from I is equal to 1 to n of Ri Ci. So it's just the sum of the time constants. And then we take the reciprocal of that. So this is different than the summation that we did at low frequencies. At low frequencies, we added the reciprocals. Here, we're adding the time constants and then taking the reciprocal. So it is slightly different methodology. So let me redraw our original circuit just for reference since it's been a minute. So here we have R1. Here we have R2. Here is RD. CDB. CSB. CGD. CGS. And lastly, our sig, where here is VN, and up here we have VDD. We know again that CSB, our source to bulk or source to body capacitance, is going to do absolutely nothing because it's shorted on both sides. So therefore, the time constant it sees is going to be 0. So we can just throw that away, right? It sees a short circuit, so C times 0 is 0. So it shouldn't contribute to our estimation at all. So let's start by what CGS sees. So CGS is going to see, when we've zeroed out Vn, we have our resistor R sig in parallel with R1 in parallel with R2. Here is CGS. Here is VGS. GM, VGS. RD, and here is V out. So I want to be very clear here. I have open circuited the capacitance CGD, which is why we don't have a capacitor linking the input side to the output side. And I have also open circuited the capacitance CDB, which is why we don't have a capacitor in parallel with RD anymore. It should be fairly obvious that VGS in this case is 0 since there are no independent sources anywhere. So the right-hand side of this circuit does absolutely nothing to our time constant. So from this, we should see that tau GS, the time constant for our gate source capacitance, is CGS times our Thevenin resistance that we calculated earlier, which if we're just looking at this guy can see that it's going to be CGS times R sig in parallel with R1 in parallel with R2. So this one, fairly straightforward. Our gate drain capacitance, CGD, is going to see, so we're going to have R sig here's R1 in parallel with R2. CGS is now open circuited, so it's not going to show up. Here is CGD. Here is VGS. Here is GMGS. And over here, we have RD. So for this one, it's significantly more difficult to see exactly the resistance that CGD sees by inspection because we have that dependent source thrown in there. So I'm going to use the test source method, much like we did previously. So I'm going to take that capacitor out and replace it with a voltage source. So I pluck this guy out, replace it with a voltage source VX, like so. And then here's my current IX, and this is also my current IX, just to be clear. And it's hard for me personally to tell what's going on with this guy. So I'm going to redraw it one last time. Oops, come back. So starting with VX, at this node right here, which is our gate, we see our resistance R thev, which is just R sig in parallel with R1 in parallel with R2. I just want to be clear about that. This node right here is where ground was. On the other side of VX, we have the node where our current source and our resistance RD are located, right? So up here is ground. Down here is effectively, not our gate, our drain. This guy over here is our gate. So we're going to have that current source is flowing from the drain to ground. Our resistance RD is connected from the drain to ground. And our voltage VGS is connected, positive polarity terminal is at the gate. Negative polarity terminal is at ground. And so this is what we have. So this is a little bit better of an approximation, but I'm going to take it one step further and do a source transformation on my practical current source on the right-hand side, making this a simple single loop circuit that we can analyze extraordinarily easily. So I am positing, this is our current IX. This is still VGS, so we're not changing where VGS is defined in any way, shape, or form. Positive polarity on the left, negative polarity on the right from the way that my current source was oriented. This is now GM VGS times RD. And here we have RD. So before we move forward, does anyone object to what I have done here? Does anyone not following what's going on? Sure. So the positive polarity terminal for the voltage source should be located at the same place as the head of the arrow of the current source, right? So let's say that I swapped these guys around, okay? So I had my current source over here and RD over here. The head was on top, so the positive polarity terminal would have been on top, but I just slid it over. So that's why the positive polarity terminal is on the left-hand side. Does that make sense? Okay. So I have a very simple single loop circuit that you guys could analyze on probably the third day of circuits 1. So we can see that negative Vx plus Ix R thev plus Gm times Ix R thev, since from Ohm's law, that's exactly what VGS is going to be, times RD plus Ix RD is equal to 0. So from this, Vx over Ix is equal to R thev plus Gm R thev RD plus RD looks like R thev times 1 plus Gm RD plus RD. And thus, our time constant tau GD is CGD times RD plus R thev 1 plus Gm RD. All right. Now we have our third capacitance, CDB, to look at. So CDB is going to see, so we're going to have R sig R1 in parallel with R2. GM VGS RD that is the exact alarm I wake up to every morning. So we're looking in to the, or actually I don't even need that. Let's not bother with that. All right, so hopefully everybody can see that VGS is equal to 0 by inspection, which means that current source does nothing. It's an open circuit, and therefore CDB just sees RD. And from this, tau dB is CDB RD, and omega high is then approximately going to be 1 over CGS times R thev plus CGD times RD plus R thev 1 plus GM RD plus CDB RD. And when I plugged numbers into this, I got the exact same value as omega P1 using the direct method. So there is technically going to be some difference, but the difference was small enough that out to 3 significant figures, I saw no difference whatsoever. So this is a very good approximation of where our midband ends, but it tells us nothing about the poles. It tells us nothing about, or excuse me, nothing about any secondary poles or higher order poles or anything like that. It also tells us nothing whatsoever about the zeros. So this is only good for estimating where the end of the midband is. Our last method is the Miller method, okay? And so this is kind of a happy medium. It's going to neglect some information, but it is going to, at the very least, tell us where we have multiple poles and stuff like that. So if we look, let me redraw this for the 5th time, it seems. CDB. CSB. CGD. CGS. Here's V out. Here's RSig. Here is VN. I have all 4 of my high frequency capacitors in there. And again, CSB doesn't do crap. So we can easily see that there is a capacitor linking effectively our input or our gate to our output, which is at our drain, right? So this would be a perfect place to use the Miller approximations that we did when we started all this kind of good stuff. So if I draw just my simple small signal model for this guy, where I have VThev applied to some resistance RThev. Here's node X. CGS. Source is grounded. GM, VGS, RD, CDB. Here's V out. I'm gonna call this guy node Y. And I have right now some capacitance between my gate and my drain, right? So if I apply Miller's theorem, I can say that this guy turns into this. CGS in parallel with a capacitance I'm going to call CGDX, where this is my voltage VGS, and then completely disconnected over here on the right-hand side, I have GM VGS in parallel with RD, in parallel with CDB, and now in parallel with some CGDY. Here is my output. And all this jibber jabber down here is ground. Where I just want to be clear, using the Miller theorem, the impedance 1 over S CGDX is the same as 1 over SCGD times 1 plus the voltage gain of our, or excuse me, 1 minus the voltage gain of our circuit. Where since this is a common emitter amplifier with no source to generation, That's just GMRD or negative GMRD. So this part is going to be 1 minus K as we defined it when we talked about the Miller effect is here going to be 1 plus GMRD. So we call this the Miller multiplication factor. And from this, we can see that CGDX is just 1 plus GMRD times CGD. So the Miller effect is making that capacitor look significantly larger on the input side of things, okay? So this is probably going to give us a rise to our dominant pole because it's the largest capacitance, which means, or it seems like it's going to be the largest capacitance, and it's tied to the input, so it should be at the lowest frequency. If we look at CGDY, we are going to have 1 over S CGDY is equal to 1 over SCGD times 1 plus 1 over GMRD. And if GMRD is much greater than 1, then this just looks like another factor of CGD tied to our output. So CGDY is going to be CGD times 1 plus 1 over GMRD. And I can say this is approximately equal to CGD if GMRD is much greater than 1. All right, so what do I want to do first? All right. So the analysis of this circuit should be fairly straightforward, right? V out is just going to be GM VGS times these three guys, these three impedances in parallel, with a factor of -1 thrown in there because the current flowing into the negative polarity terminal. And we should be able to get VGS just using simple voltage division. So this Miller effect is allowing, using the Miller effect, or Miller's theorem, is allowing us to greatly simplify the analysis. We're still going to see that we're going to wind up with 2 poles, one of which is going to look very familiar with our doing it the extremely long way. The other is going to look a little less familiar, but we are going to turn out we're not going to see any zeros. So that's one of the downsides of this. So just for completion's sake, let's say that VGS is, let me give myself more room here, actually. Using voltage division, VGS is VThev. Our numerator is going to be those 2 capacitors in parallel, right? So that's going to look like S CGS plus 1 plus GMRD CGD. And then down here in our denominator, we have RThev plus that exact same thing. S CGS plus 1 plus GMRD CGD, close my parentheses. If I multiply through by a factor of S times CGS plus 1 plus GMRD CGD, this gives me, oops, Go away. Go away. Go away. Dumb thing. There we go. Oh my goodness. VThev divided by 1 plus S Rthev CGS plus 1 plus GM RD CGD. And let me close that parentheses there real quick. The out, bless you, is negative GM VGS times so we're going to have RD multiplied by 1 over S times CDB plus 1 over GM RD CGD divided by RD plus 1 over S CDB plus 1 over GM. So just to be clear, I'm just saying I have a resistance in parallel with a capacitance, and so I'm multiplying the impedances in the numerator and adding them in the denominator. And because my two capacitors are in parallel, I can squish them together first before I throw in the S there to make the math a little bit easier. So obviously multiplying by, yes, Nathan. Oh, okay, yes. I see what you're saying. Yeah, so that 1 over GM, it should be 1 over GM RD, yes. 1 over GM RD, thank you. Yes. If I multiply through by the denominator of the numerator over the denominator of the numerator, this just simplifies to negative GM VGS times RD over 1 plus SRD CDB plus CGD times 1 plus 1 over GMRD, close parentheses there. And now I have enough information to get my entire transfer function. So V out over V thev, which is going to be close enough. It's going to tell me what my poles are and all that kind of stuff, because my relationship between Vn and V thev is purely resistive, is just negative GMRD over 1 plus S R thev CGS plus 1 plus GMRD CGD. And then over here, I have 1 plus SRD. Sorry, this should be CDB plus CGD times 1 plus 1 over GMRD, close parentheses, close brackets, leading us to a pole at 1 over R thev times CGS plus 1 plus GMRD CGD, and a second pole, omega P2, at 1 over RD times CDB plus CGD GD times 1 plus 1 over GM/RD. All right, so that's the Miller method. So we see two poles, we don't see any zeros, and this omega P1 is going to be very, very similar to what we saw before. It's actually just missing a small factor. Like we have R-Thev times, so we have 1 plus GM/RD CGD R-Thev plus R-Thev CGS. So just scrolling way back up here. We're just missing that RD times CGD plus CDB term. So the Miller approximation gives us very close to what we would get here, except we're missing this middle term. The second pole looks very, very different, obviously, so it's very hard to draw any sort of comparison. The Miller approximation typically slightly overestimates the location of the pole. And so what I mean by that is using the direct method and the method of open circuit time constants, I got the location of the first pole frequency to be at about 13.8 megahertz, and the Miller method told me it was at 14. So it's just a little bit off. All right, so I feel very strongly that we have beaten the common emitter amplifier to death, all right? Everything that we learned here, we could obviously use on, or excuse me, the common source amplifier, and everything that we learned here, we could use on the common emitter amplifier as well, but there is a pesky term which Dr. Batari kind of glossed over in the lab. If you develop that transfer function, there's going to be a R pi plus 1 plus blah, blah, blah over R Thev plus R pi plus blah, blah, blah mixed in there as well, which is going to be close enough to 1 to make these circuit analysis tools a 1-to-1 ratio for most frequencies. So let's take a look at, that's not what I wanted to do, but your web work real quick. Just the first couple of problems, because that's technically all we've covered. That being said, what we've done is applicable to any of them, so you can easily get ahead. Oh, wait, I just want to look at it. So problem 1, this is a Bjt amplifier. So this guy looks like a common emitter with no source degeneration or emitter degeneration whatsoever. So we should expect to see a single pole. So this problem asks us to find the magnitude of the low frequency pole in 0 for the above amplifier. So do you guys feel that you would be comfortable enough doing something like that? What method would you use? So in this case, direct analysis and the method of short circuit time constants should give you literally the exact same answer, since there's only one capacitor in the system. So there cannot be any capacitive interactions that we are missing by not directly analyzing this guy, since there's only one capacitance. So either way should be sufficient. That you won't get the 0 if you do that method. But I believe since there's only the one capacitor here, the 0 is going to occur at 0. So yeah. So this one is easy enough. If we look at problem 2, we have the exact same circuit, but now we're looking at, we're asked to find the amplifier's 2 high frequency poles. So to be clear here, we're looking for high frequency poles, which means this Cn is actually a short circuit, and we're looking for the poles due to the high frequency capacitances. For this Bjt model, there's going to be 3 of them. There's going to be C mu, C pi, and CS collector to bulk. So since you're asked to find the 2 high frequency poles, the best guess here is that they're looking for you to do a Miller approximation, because that'll get you there the fastest. So yeah, you couldn't use the open circuit time constant method because that's only going to give you 1 pole, so you're still going to be missing information. Direct analysis on this would just be terrifyingly annoying. So I would say use Miller's theorem and get there. And then if we go into the subsequent problems, let's see, this guy is a common base. Not there yet. We'll develop that on Monday. Same common base amplifier, but high frequency. This is a source follower. We'll probably get there on Monday as well. And then we have a Cascode. So you can easily do the first 2. You could probably struggle your way through the second 2 with the knowledge that you have. All right, so unless anybody has any questions, that's enough out of me for today. So you get to, I don't know, go away 20 minutes early. Yeah. Yeah. All right. Yeah. All right. See you guys on Monday. Have a good weekend.